A modern city can be leveled in minutes by the Earth's fury, yet a stone temple from 2,000 years ago stands untouched. This is the profound paradox of seismic engineering. By the end of this journey, you will see these ancient structures as the most sophisticated survival manuals ever written in stone. How did builders without computers design for forces they could not see? What hidden language of stability did they carve into their sacred sites? The answers reveal a forgotten conversation between human creativity and planetary power. What does our own future look like if we choose to listen to the wisdom in these old stones? In 2010, a single earthquake in Haiti collapsed over 200,000 structures in moments, a tragedy of almost incomprehensible scale. Yet on the other side of the world, the Parthenon in Greece has withstood not one but dozens of major quakes across 2.5 millennia. Its columns still hold the sky, a silent rebuke to our modern assumptions. How can a building from the age of philosophers outlast cities built with steel and paradox of permanence that lies at the heart of our story? It suggests a profound disconnect, not in our technology, but in our fundamental approach. Ancient builders did not have seismographs or engineering degrees. What they possessed was something perhaps more powerful, a deep, accumulated knowledge forged through direct and often devastating experience. This is called vernacular engineering. It is not a single grand theory written in a textbook, but a living library of solutions, refined by trial and observation, and passed from master to apprentice over countless generations. Every crack in a wall, every tremor felt in the feet became a data point. Every failure taught a lesson that was woven into the next temple, the next city wall. The question we must ask is not whether these methods worked, for the stones themselves are the proof. The real mystery is one of intention. Were these ingenious adaptations merely happy accidents stumbled upon over centuries? Or did these cultures develop a sophisticated, intuitive understanding of the Earth's behavior, a physics expressed not in equations but in the placement of a stone and the choice of a mortar? To find the answer, we must learn to read the architecture not as a static monument, but as a dynamic conversation with the planet. The first secret lies not in the walls but beneath the feet. It is the art of letting the Earth move. Modern skyscrapers achieve this with complex systems of rubber bearings and sliding plates, a technology we call base isolation. Yet the core idea is ancient, a whisper passed down through stone. Builders from worlds apart discovered that to save a temple, you must first set it free. They did this by creating a flexible foundation, a deliberate weakness that became the structure's greatest strength. Imagine a massive pyramid not resting on solid bedrock, but seemingly floating on a deep, prepared bed of crushed stone, sand, or gravel. When the ground shakes, these granular layers shift and roll, absorbing and dissipating the energy like a shock absorber. The violent horizontal lurch of the Earth is transformed into a far gentler, filtered motion by the time it reaches the structure above. It is a brilliant paradox, stabilizing a building by first allowing it to be unstable. In Mesoamerica, Aztec engineers used a lightweight, porous volcanic rock called tezontle in their foundational layers. This material compressed and shifted, acting as a natural buffer. Across the ocean, the builders of ancient Greek and Mycenaean temples often placed their first courses of stone on a layer of sand or clay. The principle was the same, to decouple the rigid monument from the trembling ground. This is not a crude approximation of modern science, it is the very essence of it. These cultures observed that rigid connections break. They learned that sometimes survival means knowing when not to fight the force directly, but to redirect it, to let it pass through and around. The temple, in a very real sense, was taught to dance just enough to avoid being knocked down. This fundamental insight, written in gravel and sand, asks us to reconsider what true strength looks like. Is it unyielding rigidity, or is it resilient flexibility? The stones have voted, and their verdict has stood for thousands of years. The second secret is written in the very joints between the stones. It is the genius of interlocking masonry, a three-dimensional puzzle of such precision it seems to defy the tools of its age. Walk among the ruins of an Inca citadel like Machu Picchu, or run your hand along the foundation of a classical Greek temple. You will not find simple, rectangular blocks stacked like bricks. Instead, you see a complex mosaic of polygonal and trapezoidal shapes, each face carved to match its neighbor with astonishing accuracy. These stones were laid without mortar, a technique known as dry stone or ashlar masonry. But this was not a primitive shortcut. It was a deliberate and sophisticated seismic strategy. Think of it as nature's own Lego system, designed not for rigidity but for controlled movement. During an earthquake, the ground does not shake in a uniform way, it writhes and twists. A rigid, mortared wall tries to resist this twisting as a single, solid unit, and when the force exceeds its strength, it cracks and fails catastrophically. The interlocking dry stone wall behaves entirely differently. Each uniquely shaped block is locked in place by its neighbors on multiple sides, distributing any incoming force across a network of contacts. When the tremor hits, the entire structure has a tiny amount of give. The stones can shift, rotate, and settle microscopically within their joints, dissipating the seismic energy through friction and movement. Then, as the shaking subsides, gravity and their interlocking shapes guide them back into place, like a puzzle gently reassembling itself. The wall breathes, it dances, and it survives. The level of craftsmanship required for this is staggering, speaking to a deep, empirical understanding of material behavior under dynamic loads. Builders learned through observation that perfection was not about creating a monolithic, unyielding form. True resilience was found in a system of many individual parts, masterfully crafted to work together under immense stress, allowing the structure to flex without breaking its bonds. This ancient insight mirrors principles in modern engineering, where expansion joints and flexible connections are deliberately built into bridges and skyscrapers. The stones of Machu Picchu, silent for centuries, were already teaching that lesson, a testament to the power of connection over sheer mass. The third secret turns our intuition about stability completely on its head. It is the strategic, almost playful use of weight and a high center of gravity. Look at a traditional Japanese pagoda, soaring 5 or even 7 stories into the sky. In a typhoon or an earthquake, it does not stand stiff and defiant. It sways, it rocks, it moves with a slow, graceful rhythm, like a giant tree bending in a powerful wind. The miracle is that it always returns to center, never toppling. This dance of survival is orchestrated by 2 brilliant design choices. First, deep within the hollow core of the pagoda, from the foundation to the pinnacle, hangs a massive, free-standing central pillar called a shinbashira. It is not a load-bearing column in the conventional sense. It does not hold up the floors. Instead, it acts as an enormous pendulum. When the building sways, this heavy pillar swings within its own space, its inertia pulling against the motion, slowing the oscillation, and helping to drag the entire structure back to vertical. Second, and more counterintuitive, is the roof. Each tier of a pagoda is crowned with an incredibly heavy, ornate roof made of clay tiles. Architects deliberately placed this immense weight high above the ground. In a static world, a high center of gravity is a recipe for disaster, making a structure top-heavy and prone to tipping. But in the dynamic, shaking world of an earthquake, that same weight becomes a masterful tool for control. The physics are elegant. The heavy top cannot change direction quickly. It resists the rapid, jerking motions of the seismic waves, effectively damping the energy and forcing the building into a slower, more manageable rocking motion. It is the difference between a quick, sharp jerk that snaps a twig and a long, slow swing that a tree can withstand. This principle of using mass as a dynamic counterweight appears across cultures. The massive, multi-tiered stone roofs of ancient Chinese temples, with their sweeping, upturned eaves, serve a similar purpose. All that stonework is not merely decorative grandeur, it is a precisely calculated inertial damper. The builders understood that to control a chaotic force, you sometimes need to meet it with a greater, slower force of your own. They used weight not as a burden to be overcome, but as a partner in a delicate balancing act. In these structures, gravity itself was recruited from a potential enemy into the greatest ally of all, a constant, silent hand guiding the temple back to stillness after the storm passes. This leads us to a fourth secret, one that seems almost counterintuitive to the modern mind. Ancient engineers mastered the art of planned sacrifice. They designed their temples with deliberate weak points, elements meant to fail first in order to save everything else. This philosophy of controlled damage is a profound lesson in humility and foresight. It acknowledges that some forces are too great to resist completely, so the wisest course is to manage the collapse. In classical Greek and Roman architecture, this principle is embodied in the metal clamps and wooden dowels used to connect massive stone blocks. These connectors were not the strongest part of the assembly, they were often the weakest. When a powerful tremor struck, these metal or wood links would bend, shear, or break, absorbing a tremendous amount of destructive energy in the process. This sacrificial failure acted exactly like a fuse in an electrical circuit, blowing itself to protect the more valuable and irreplaceable stonework. The structure would suffer localized damage, but the core integrity remained, preventing a total, catastrophic pancake collapse. This strategy extended to the overall layout. Consider the grand colonnade surrounding a temple, a forest of stone columns. These columns were not locked together into a single rigid cage. Instead, each stood with a degree of independence, connected only by the horizontal beams above. During an earthquake, individual columns could tilt, rock, or shift in their sockets without dragging their neighbors down. This prevented a chain reaction where the failure of one element triggers the failure of all. The entire system was designed to degrade gracefully, to give way in a predictable, non-catastrophic sequence. This approach provided two life-saving benefits. First, it gave people inside precious extra moments to escape, as the building groaned and settled rather than instantly imploding. Second, it made repair possible. Replacing a few broken bronze clamps or resetting a tilted column was a manageable task. Rebuilding an entire temple from rubble was not. This ancient insight, this willingness to design for failure, stands in stark contrast to a modern mindset that often prioritizes unyielding strength at all costs. It recognizes that true resilience is not about being indestructible, but about being repairable. It is about creating structures that can be wounded and still stand, that can tell the story of the storm they weathered in their scars and be ready to face the next one. The geometry of these ancient temples holds a fifth, silent secret, a language of stability written in angles and inclines. Stand before the monumental gateway of an Egyptian temple, a pylon, and your eye is drawn upward by its soaring height. But look closer at its profile and you will see a subtle, powerful truth. The walls are not parallel, they are thicker at the base and steadily taper as they rise. This is not an aesthetic whim, it is a fundamental law of physics made visible in stone. The pyramidal form, seen in ziggurats and pyramids worldwide, deliberately lowers the structure's center of mass, pulling its gravitational heart closer to the ground. In a seismic event, this is a decisive advantage. A lower center of mass makes a structure far less likely to topple, like a weighted bottom on a child's toy that always rights itself. The tapering wall does something else equally brilliant. It channels force. The immense weight of the stone above creates a continuous, downward compressive force that flows along the slanted faces, pushing inward and downward into the foundation. This compression actually locks the stones together more tightly under stress, turning the wall's own mass into an active stabilizing agent. This geometric intuition extends to the very columns that hold the roof. Look at the Parthenon's famous colonnade with an engineer's eye, and you will discover they are not perfectly vertical plumb lines. Each column has a barely perceptible inward lean, and the entire platform they stand on curves slightly upward in the center. This was a breathtakingly sophisticated choice. During an earthquake, when lateral forces try to push the columns outward, their inward inclination works against that motion. The shaking force is translated into increased compression along the column's axis, essentially making the column want to stand up straighter under the load. It is a masterful bit of counterintuition, using the earthquake's own energy to strengthen the structure's resolve. Furthermore, the slight curve of the temple's base, rising toward the center, meant that during a tremor, the columns would rock on their foundations and tend to settle back toward the middle of the platform, a self-centering mechanism crafted from stone. What we are witnessing in these tapered walls and inclined columns is a profound understanding of force redirection. Ancient builders thought in vectors long before the word was invented. They shaped their stones to guide the chaotic, horizontal energy of an earthquake, merging it with the constant, vertical pull of gravity and funneling that combined force safely into the earth. They turned potential weaknesses, like the height of a wall or the slenderness of a column, into strengths through nothing more than clever shaping. This represents the pinnacle of vernacular engineering, where observation of the natural world, trial and error across generations, and an almost artistic sensibility for form coalesced into architecture that could argue with the planet itself. The temple was not just built on the land, it was designed as an extension of it, its geometry a direct response to the land's hidden capacity for violence. This silent conversation between form and force is why, when the ground ceases its trembling, these stones are still holding their silent, elegant pose against the sky. Perhaps no ancient site embodies this deep integration more powerfully than the Temple of Apollo at Delphi. For centuries, it was considered the very center of the world, a place where mortals could speak directly to the gods through the cryptic prophecies of the Pythia, the oracle. What modern geology has revealed is that this spiritual epicenter was also a literal geological one. The temple was constructed deliberately on the slopes of Mount Parnassus, straddling a major, active fault line. This was not a catastrophic oversight, but a breathtaking act of synthesis. The same tectonic fractures that made the ground shudder also released vapors, gases like ethylene that seeped from a rocky chasm beneath the temple. Historical accounts describe the Pythia inhaling these vapors before delivering her prophecies, entering a trance-like state. The divine voice, it seems, was quite literally breathed from the earth itself. Here, the seismic zone was not a threat to be mitigated in isolation, but a sacred source of power to be harnessed and revered. The architecture had to accomplish a dual purpose. It had to facilitate this profound spiritual connection while simultaneously surviving the ground's instability. The builders achieved this through adaptive foundations. They constructed a complex, layered base for the temple, using retaining walls and terraces to stabilize the sloping, fractured ground, essentially creating a massive, engineered platform upon which the sacred structure could safely sit. This was more than just clever engineering. It was a philosophical statement carved in stone. The people of Delphi did not see the fault line as a problem. They saw it as a feature, a vital conduit between realms. Their building techniques were not about dominating nature, but about engaging in a respectful, informed dialogue with it. They listened to the whispers of the earth, the tremors and the gases, and wove those forces directly into the cultural and spiritual heart of their civilization. This holistic view stands in stark contrast to our modern tendency to separate, to compartmentalize. We often see geology as one field, spirituality as another, and engineering as a third, a tool to impose our will upon the first. At Delphi, these were not separate disciplines. They were different expressions of the same fundamental truth, that the world is alive, interconnected, and speaking to those who know how to listen. The temple's endurance is a testament to that listening, a structure that did not fight its location but was fundamentally conceived by it, a perfect fusion of sacred purpose and seismic reality. Yet this principle of dancing with the tremor finds its most elegant and enduring expression in the wooden pagodas of Japan. The Horyu-ji Pagoda, a 5-story wooden tower, has stood for over 1,400 years. In that time, it has endured countless earthquakes, typhoons, and wars, never collapsing. Its survival is not a matter of luck, but of a radical engineering philosophy made physical. At first glance, the pagoda seems impossibly fragile, a delicate lattice of wood reaching for the sky. Its true strength, however, lies in its deliberate flexibility, a carefully choreographed dance of give and take. The core of this system is an intricate network of interlocking wooden brackets known as Tokyo. These are not simple nails or rigid joints. They are complex, layered assemblies that connect beams and columns with a brilliant combination of strength and play. Each bracket acts like a flexible, wooden handshake, allowing for a tiny amount of movement at every connection point. This design means that each of the pagoda's 5 stories is not locked rigidly to the one below it. Instead, they can sway independently during a tremor. Imagine a stack of broad-brimmed hats. If you shake the base, the hats will tilt and slide against each other, but they are unlikely to topple over as a single, stiff unit. That is the pagoda's secret. It is not one rigid tower, but a series of loosely coupled, flexible boxes. The seismic energy from the ground does not travel upward in a single, destructive wave. It is dissipated at each level as the stories sway out of sync with one another, the friction in the wooden joints converting the violent shaking into harmless heat and gentle motion. Then there is the central pillar, the shinbashira. In many pagodas, this massive timber column hangs from the roof structure, its base hovering just above the ground or resting lightly in a shallow socket. It is not a load-bearing column in the conventional sense. It is a giant, suspended pendulum. When the pagoda sways, this heavy pillar swings within the hollow core, its inertia acting as a counterweight that dampens the oscillation and helps pull the entire structure back to center. The entire system is a masterpiece of energy management. It does not resist the earthquake's force. It welcomes it, absorbs it, and transforms it into a slow, rhythmic rocking that the wood can endure. This ancient wooden technology is so profoundly effective that it directly informs how we build today. Modern engineers studying seismic resilience look to these pagodas for inspiration. The principles of flexible joints, energy-dissipating layers, and tuned mass dampers like the central pillar are now engineered into the steel and concrete of skyscrapers in Tokyo and San Francisco. The Horyu-ji Pagoda is more than a beautiful relic. It is a living, breathing textbook, its silent dance across the centuries continuing to teach us how to build a future that can bend without breaking. Machu Picchu does not simply occupy its mountain ridge. It is an extension of the mountain's own logic. This citadel, suspended between sky and cloud, is perhaps the most complete expression of ancient seismic wisdom ever constructed. While its dry stone walls are rightly celebrated, the true genius of the site lies beneath them, in a foundational act of terraforming so vast it reshaped the entire mountain slope. The Inca did not just build a city on a ridge, they first had to invent a stable ground for it to stand upon. The steep, unstable terrain was a recipe for disaster, prone to catastrophic landslides, especially during the violent shaking of an earthquake. Their solution was both monumental and elegant. They carved the mountainside into a cascading series of hundreds of terraces. But these were not simple agricultural steps. Each terrace was a sophisticated engineering unit. Workers excavated deep into the slope, then laid a foundation of crushed stone, building upward with layers of smaller stones, gravel, and sand before topping it with rich soil. This created a deep, free-draining, granular base for every single structure above. Think of the entire mountainside beneath the temples and houses not as solid earth, but as a giant, layered mattress. When seismic waves rippled through the bedrock, this engineered fill absorbed and dissipated the energy. The individual particles within the gravel beds shifted and rolled, dampening the tremor's force before it could reach the buildings. This was landscape-scale base isolation, a shock-absorbing foundation carved into the earth itself. The terraces also solved the ever-present threat of water, the primary trigger of slope failure. An intricate network of drainage channels woven through each terrace layer ensured that torrential rain would percolate down and flow away, never allowing water pressure to build up and liquefy the ground. This dual function is breathtaking. The same system that kept the mountain from washing away also kept it from shaking the city apart. Upon this stabilized, living foundation, the Inca then constructed their iconic walls. The famous fit of the stones, so precise that even a thin blade cannot penetrate the joints, is not about creating a monolith. It is about creating perfect, friction-locked connections. Without mortar, each stone is held by the precise geometry and weight of its neighbors. During an earthquake, this entire assembly can flex and sway minutely, the stones grinding against each other, converting the destructive energy of the shake into harmless friction and heat. The walls breathe as a single, flexible skin, settling back into place once the tremor passes. What we witness at Machu Picchu is a holistic philosophy of resilience. The Inca engineers saw no separation between the structure and the site. They understood that to protect the building, you must first heal the land it sits on. They transformed a treacherous, dynamic mountainside into a regulated, responsive platform. The city is not a foreign object placed upon the landscape. It is the landscape, refined and perfected into a sanctuary. This is the ultimate lesson from the clouds. True stability is not about defying nature's forces, but about intelligently redirecting them, about building with the mountain, not just on it. In every perfectly fitted stone and deep drainage terrace, we see a dialogue with the earth so profound that after 5 centuries of earthquakes and storms, the conversation is still peacefully ongoing. Roman concrete holds a secret that modern science is only now beginning to fully unravel. While their temples were often adaptations of Greek designs, their revolutionary building material, used in structures like the Pantheon and the aqueducts, reveals a mastery of both chemistry and physics. The key ingredient was not found in a quarry but in a volcano. They mixed lime with a fine volcanic ash called pozzolana, sourced from regions like Pagoda. This combination created a chemical reaction that continues for centuries. Unlike modern concrete, which can weaken as water infiltrates and cracks form, Roman concrete does the opposite. When tiny fractures appear and rainwater seeps in, it reacts with the leftover lime and pozzolana in the mix, forming new mineral crystals that literally glue the crack shut. The material does not just resist damage, it actively repairs itself, growing stronger with age. This is not a metaphor, it is a verifiable chemical process, a built-in healing mechanism that has kept structures standing for 2 millennia. It represents a philosophy of endurance through adaptability, where the material itself is designed to evolve and respond to its environment, much like living tissue. This chemical genius was paired with a revolutionary structural form, the arch. The Romans did not invent the arch, but they perfected and deployed it on an unprecedented scale. from the soaring vault of the Pantheon to the stacked galleries of the Colosseum. The arch is a shape of profound strength because of how it manages force. Unlike a straight stone lintel, which can crack under its own weight, the curved arch channels the load downward and outward along its curve, transforming crushing downward pressure into a lateral thrust that is then caught and supported by massive piers or adjacent arches. This elegant redistribution avoids points of concentrated stress, the weak spots where failure typically begins. In a structure like the Colosseum, this principle was multiplied into a resilient three-dimensional network. Its iconic facade is not a solid wall, but a lattice of arches upon arches. When an earthquake struck, this open, repetitive design allowed the entire amphitheater to flex. The network of arches could sway and shift slightly, each arch helping to redistribute the seismic forces to its neighbors, effectively sharing the burden across the entire framework. It could bend without breaking, its very geometry acting as a shock-absorbing skeleton. The combination of self-healing concrete and flexible, load-sharing arches created a synergy of resilience. One addressed the microscopic world of material decay, the other managed the macroscopic forces of gravity and tremor. Together, they demonstrate a holistic understanding of durability that considered both the chemistry of the stone and the physics of the form. Today, material scientists are actively studying Roman concrete recipes to develop modern self-healing versions, hoping to endow our infrastructure with that same ancient longevity. In the silent, enduring presence of the Pantheon's dome, we are witnessing a conversation between human ingenuity and the elements that has not yet reached its final word. A sudden change of plan is written in stone 4,500 years ago. The bent pyramid at Dosha in Egypt rises from the desert with a startling silhouette, its lower half climbing at a steep, aggressive angle before abruptly shifting to a gentler, more cautious slope near the top. This is not a design quirk or an artistic flourish. It is a frozen moment of crisis and adaptation, a monumental lesson learned in real time. The prevailing theory among Egyptologists and engineers is that as the pyramid's first phase neared completion, the builders witnessed alarming signs of stress. Cracks may have appeared in the internal chambers, or the outer casing stones began to shift, signaling that the ambitious 54-degree angle was creating unsustainable pressure within the structure. The steep incline concentrated too much weight, risking a catastrophic collapse. Faced with this imminent failure, the architects did not abandon their project. Instead, they performed one of history's most audacious mid-construction corrections. They changed the fundamental geometry of a royal tomb already reaching toward the heavens. From the bend upward, the angle was reduced to around 43 degrees, a shallower slope that distributed the immense weight of the stone more evenly and lowered the structure's center of gravity. This was a pragmatic, physics-driven decision, a direct response to observed structural performance. It represents a profound shift from rigid dogma to flexible problem-solving. The bent pyramid stands as perhaps the world's oldest and largest documented experiment in seismic and structural engineering. Its unusual shape is a testament to the idea that resilience is not about never making a mistake, but about having the wisdom to recognize one and the courage to change course. The builders listened to the whispers of the stone, and in doing so, they created a monument that has not just endured, but has taught a silent lesson across 45 centuries, that true stability often requires the humility to bend. The bent pyramid's change of course reveals a culture learning from the physical world. Yet for many ancient societies, the line between the physical and the spiritual was beautifully blurred. The enduring strength of a temple was never seen as just a triumph of engineering. It was a sign of divine favor, a testament to a sacred covenant between the people and their gods. This belief, however, was not a passive superstition. It often acted as a powerful cultural engine that actively preserved the very engineering it celebrated. Think of the meticulous astronomical alignments built into temples from Stonehenge to the Great Pyramid. To keep a stone corridor perfectly aimed at a star that rises only once every year for centuries, you need a foundation that does not shift by even a fraction of an inch over generations. The sacred goal of tracking the heavens demanded, and therefore inspired, an unparalleled standard of geotechnical stability. The spiritual purpose literally dictated the engineering rigor. This created a powerful feedback loop, where the success of the ritual proved the soundness of the construction, and the enduring construction reinforced the power of the ritual. This intertwining extended to the rituals themselves. Grand ceremonial processions that circled a temple or climbed its terraces were acts of worship, but they were also informal, recurring structural inspections. As priests and pilgrims moved along prescribed sacred paths, they would naturally observe the condition of the walls, the steps, the drainage channels. A crack noticed during a festival became a communal concern, a flaw in the divine dwelling that required immediate remedy. The knowledge of how to repair the distinctive mortar or how to reset a specific type of carved block was not stored in a manual. It was carried in the hands and memories of the artisan families who served the temple generation after generation. Their skills were maintained and passed down because the temple was not a completed project. It was a living entity, a body that required constant care to house the spirit within. This cultural imperative for maintenance is a force modern archaeology often overlooks. We marvel at a 2,000-year-old building, but we forget it likely never went 50 years without some form of careful attention. A loose stone was reset, a clogged drain was cleared, a weathered surface was replastered, all as acts of piety. This sustained stewardship meant small problems were solved before they could become catastrophic failures. The temple was kept in a state of continuous, gentle repair, its resilience actively nurtured by the community it served. In this light, the temple's longevity becomes a story of sustained relationship. Its survival was not just baked into the original mortar, but woven into the annual calendar, the religious duties, and the collective identity of the people. The physics of the interlocking stones gave it the ability to withstand an earthquake, but the culture of reverence gave it the ongoing will to do so. The structure was loved, watched, and tended. This transforms our understanding from seeing these as inert ruins of a lost civilization to recognizing them as the longest-running collaborative projects in human history. They stand today not because they were abandoned to time, but because for centuries they were never abandoned at all. This deep cultural investment raises a poignant question for our own world. What do we build today that we are committed to maintaining for 1,000 years? What structures are so woven into our identity that we would instinctively, generation after generation, ensure their care? The ancient temple's greatest secret may be that its most critical component was not stone or mortar, but memory, and the unwavering human desire to preserve a connection to something greater than ourselves. Water itself may have been the most elegant shock absorber of all. Beyond the solidity of stone and the flexibility of wood, ancient engineers harnessed the liquid mass of the earth in a profound act of seismic alchemy. Scattered through historical records and the silent layouts of sacred sites are clues pointing to a forgotten technology, where the very pools and moats built for spiritual reflection served a hidden, stabilizing purpose. Consider the vast, mirror-like reflection pools that stretch before the temples of Angkor Wat. For centuries, they were seen as symbols of the cosmic ocean, a perfect surface to double the majesty of the stone towers above. Yet their placement and scale suggest another, more terrestrial function. A large body of water is not passive, it is a massive, slow-moving weight. When the ground shakes, the water within a broad, shallow pool does not move in unison with the tremor. Instead, it sloshes, its own natural rhythm dictated by the pool's dimensions. If the pool is sized correctly, this sloshing frequency can be deliberately tuned to be out of phase with the natural vibrational frequency of the temple itself. The result is a phenomenon of cancellation. As the building tries to sway one way, the heavy, delayed motion of the water pushes against it, damping the oscillation like a hand gently steadying a swaying bowl. This is not magic, but an intuitive application of harmonic physics, using the environment itself as a counterweight. The principle extends to the sacred lakes that once bordered many Egyptian temple complexes. These were not mere decorative reservoirs, they were immense, excavated basins holding millions of gallons of water. Their primary purpose was ceremonial, for ritual purification, and as symbolic representations of the primordial waters of creation. But their secondary effect was one of profound geotechnical stabilization. The sheer mass of that water pressing into the earth could help consolidate loose, sandy soils, creating a more stable platform. More subtly, during a seismic event, the inertia of that vast liquid mass would resist rapid movement, acting as an inertial anchor for the entire precinct. The temple was not just built near water, it was, in a very real sense, moored to it. This idea transforms our understanding of these features from purely symbolic to multifunctional masterstrokes of design. It reveals a mindset that saw no conflict between the sacred and the practical. The pool that cleansed the soul also, quite literally, steadied the ground upon which the soul stood. It was a holistic solution where beauty, ritual, and resilience were woven into a single, seamless expression. This hints at a lost chapter in engineering history, where the intuitive understanding of natural forces reached a level of sophistication we are only now rediscovering through our own equations. It asks us to look again at the serene surfaces of ancient waters, not just as mirrors to the heavens, but as silent, liquid guardians that have helped calm the trembling earth for 1,000 years. The stones themselves were chosen with a quiet, profound intelligence. Ancient builders were master material scientists, conducting a millennia-long experiment with the very bones of the earth. They did not merely pick a rock for its color or ease of quarrying. They selected it for its inherent personality, for how it would behave under the immense, dynamic pressures of a trembling world. This was an intuitive science born of deep observation and hard-won experience. A builder would know that granite, with its dense, interlocking crystalline structure, was peerless under compression, perfect for the foundational courses that had to bear the unimaginable weight of everything above. Yet that same hardness made it difficult to carve with intricate detail. So for the soaring columns and elaborate friezes that told the stories of gods and heroes, they might turn to limestone, a softer stone that offered beautiful workability, allowing for precision that could translate myth into form. And in regions prone to constant, subtle movement, a flexible sandstone might be chosen, its granular composition allowing it to absorb shock without shattering. Each stone was a strategic decision, a piece in a larger puzzle of resilience. This empirical knowledge extended brilliantly into the world of timber. In the pagodas of Nepal and the tiered temples of Kyoto, the choice of wood was never arbitrary. Builders selected species like sal wood, renowned not just for its durability, but for its specific mechanical gifts, its high tensile strength and natural flexibility. This wood could bend like a bow under stress, storing and releasing energy without snapping. It had a kind of memory, wanting to return to its original shape. In a seismic zone, this was not just a building material, it was a partner in survival. These ancient artisans understood concepts like fatigue resistance and energy dissipation through the feel of grain and the sound of a strike. They knew which timber would grow and settle over centuries without failing, which stone would lock tighter under pressure. They were reading nature's own engineering manuals, written in the density of grain and the fracture patterns of rock. They chose not the strongest material in an absolute sense, but the right material for the right job, creating a harmonious assembly where each component played to its natural strengths. This deep material wisdom meant the very fabric of the building was pre-adapted to dynamic forces. The temple was not fighting its own composition. It was engineered from the inside out, its resilience woven into the selection of every block and beam long before the first foundation was laid. This principle of isolation did not end at the foundation of a single building. It scaled upward, governing the layout of entire sacred cities. In sprawling temple complexes, ancient planners engineered a landscape of intentional separation. Individual shrines, halls, and colonnades were not fused into a single, rigid megastructure. Instead, they were carefully positioned as independent islands, connected by open courtyards, stepped walkways, or bridges with deliberate gaps. These spaces were not merely for procession or aesthetics, they were seismic firebreaks. Their purpose was to fragment and contain the destructive path of an earthquake's energy. When the ground shook, each building could sway, rock, or settle according to its own rhythm and design, without being forced into a catastrophic dance with its neighbor. The shockwave, unable to travel unimpeded through a continuous structure, would lose its force in the open air between them. Damage was quarantined, limited to a single section rather than rippling through the entire holy site. This is the concept of a seismic gap, a planned void that becomes a life-saving buffer. Nowhere is this masterful urban planning more visibly eloquent than on the Acropolis in Athens. Stand upon that sacred rock and you see a collection of masterpieces, not a fused fortress. The Parthenon, the Erechtheion, the Temple of Athena Nike, each stands proudly apart, anchored directly to the bedrock but independent of one another. They are a family of structures, not conjoined twins. In a major tremor, the heavy columns of the Parthenon could tilt in their sockets without pulling the delicate porch of the maidens on the Erechtheion down with them. The failure of one, however unlikely, would not trigger a progressive collapse of all. This was a profound insight translated into city planning. It acknowledged that you could not guarantee every single component would survive perfectly, so you designed the system to compartmentalize any misfortune. The sacred precinct's resilience lay not just in the strength of its parts, but in the intelligent space between them. This ancient strategy is now a cornerstone of modern seismic engineering codes, which mandate separation joints between large building sections to prevent pounding during an earthquake. It is a direct echo of that ancient wisdom, understanding that true collective safety sometimes requires giving each element the freedom to move on its own. The Acropolis, therefore, is more than a monument to beauty. It is a preserved lesson in risk management, a stone diagram teaching us that survival is often a matter of thoughtful distance. The sky itself became a blueprint for stability. When a culture's most sacred duty was to mark the precise moment a star returned or the sun touched a specific notch on the horizon, their architecture had to be more than strong, it had to be eternally precise. A temple that shifted even a few inches over a century would break its celestial covenant, rendering its most important rituals meaningless. This spiritual imperative for perfect, unchanging alignment created an engineering challenge of breathtaking difficulty, one that demanded foundations of almost supernatural rigidity. To keep a stone corridor aimed at a star for 1,000 years, you cannot simply build on the ground, you must become one with the bedrock. This quest for cosmic connection forced builders to solve problems of settlement and tilt long before they might have otherwise, driving innovations that gave their structures a profound resistance to the Earth's sudden movements. The Great Pyramid of Giza offers the ultimate testament to this principle. Its sides are aligned to the cardinal directions with an accuracy of less than 1/10 of a degree, an orientation to true north achieved over 4,500 years ago. To accomplish this, its builders first had to create a base that was perfectly, unwaveringly level across an area of 13 acres. And they succeeded. The pyramid's foundation stones are leveled to within just over half an inch. This was not an artistic pursuit, it was a geometric and spiritual necessity. To achieve such precision, the builders likely excavated down to a stable limestone plateau, then painstakingly leveled it using a network of water-filled trenches as a giant natural spirit level. They distributed the unimaginable weight of 6 million tons of stone so evenly that the settlement has been virtually negligible across millennia. This is the hidden gift of astronomical ambition. The same deep, meticulously prepared foundation that locks the pyramid in a conversation with the stars also anchors it immovably against the lateral shove of an earthquake. The spiritual need for permanence in the cosmic realm created a physical permanence in the geological one. The pyramid does not just point to the North Star, it is rooted against the Earth's chaos with a resolve born from that very pointing. In this way, the drive to reach for the heavens produced some of the most seismically robust foundations ever conceived, a perfect marriage of celestial aspiration and terrestrial wisdom. The silent dialogue between ancient stone and modern steel is now an open conversation in engineering labs worldwide. Today's architects and seismologists no longer view these time-worn temples as mere relics. They see them as a vast, open-source database of proven solutions. The intuitive leaps made by master builders millennia ago are being rigorously tested, quantified, and reborn in our cities. In a hospital in San Francisco or a museum in Tokyo, you will find the direct technological descendant of an Inca terrace or a Greek sand bed. It is called a base isolation system, and it works on the same elegant principle, decoupling a building from the shaking earth. Instead of gravel and sand, modern versions use alternating layers of steel plates and synthetic rubber bearings. When the ground lurches, these bearings deform, allowing the entire structure above to slide gently, sometimes by several feet, while the foundation moves violently below. The building is not fighting the earthquake, it is gracefully sidestepping it, a direct translation of that ancient wisdom into high-tech polymer and steel. This is not a vague inspiration, it is a clear lineage where empirical observation has been validated by physics and scaled to protect thousands of lives. Perhaps the most poetic modern echo is found in the clouds, in skyscrapers like Taipei 101. Suspended between the 87th and 92nd floors of that towering colossus is a golden, sphere-shaped tuned mass damper. It is a 660-ton steel pendulum, the largest of its kind in the world when built. During typhoon winds or seismic tremors, this massive ball sways in the opposite direction of the building's movement, counteracting the sway just like the central pillar, the Shinbashira, in a wooden pagoda. The principle is identical, using a suspended weight as a dynamic counterbalance to dampen oscillation. The ancient Japanese carpenter understood the concept through craft and observation. The modern engineer calculates its exact mass and frequency with supercomputers. They are both answering the same fundamental question with the same fundamental tool. How do you make a tall, slender structure dance safely with the wind and the wave? This continuity is breathtaking, a thread of insight stretching from the fragrant cedar of Horyu-ji to the gleaming steel of a 21st century megastructure. What has changed is our ability to peer into the chaos. Where ancient builders refined their designs through generations of tragic trial and observation, we now use sophisticated computer simulations to model every conceivable stress. Engineers can subject a digital twin of a building to thousands of simulated earthquakes in minutes, tweaking the design to see how it performs. This allows them to refine those ancient concepts with incredible precision, optimizing the thickness of a rubber isolator or the swing of a mass damper for a specific location's unique seismic profile. Advanced materials like shape memory alloys and fiber-reinforced polymers give us new ways to achieve that ancient ideal of self-healing and flexible strength. We are not replacing the old secrets, we are giving them a new vocabulary and a greater reach. The dialogue between intuitive, vernacular engineering and analytical, computational science is creating a powerful new paradigm. It is a fusion of deep-time wisdom with cutting-edge innovation, proving that the most resilient future is one that remembers its past. This partnership suggests that the greatest structures of tomorrow may not be those that simply impose a new form upon the landscape, but those that listen, as the ancients did, to the whispers of the earth and respond with both humility and technological brilliance. A restored temple can become a trap of its own making. This is the profound ethical dilemma facing conservators today, a tightrope walk between saving a monument and unknowingly stripping it of its ancient defenses. When an earthquake damages a centuries-old structure, the instinctive modern response is to make it stronger, to bolt it back together with steel and fill its cracks with unyielding concrete. Yet this well-intentioned intervention can be a fatal misunderstanding. It risks turning a flexible, dancing survivor into a rigid, brittle statue, one that may stand perfectly still until the next tremor shatters it completely. The very systems that allowed these temples to endure, the sacrificial joints, the rocking foundations, the independent movement of stone blocks, rely on a delicate balance of give and take. Lock them down with modern, rigid materials and you disable their ancient shock absorbers. You fix the crack, but you break the mechanism. This creates a preservation paradox of heartbreaking complexity. How do you heal the wound without killing the patient's immune system? The answer lies not in overpowering the old design, but in learning its language and becoming its careful collaborator. It requires a humility that sets aside the arrogance of newer technology to listen to the wisdom of the older. Around the world, pioneering projects are showing the way, demonstrating that the most advanced restoration technique is often the most respectful one. After a devastating earthquake in 2015 severely damaged the historic temples of the Kathmandu Valley in Nepal, international teams faced this exact challenge. The temples, built with intricate wooden lattices and brick masonry, had survived centuries precisely because of their flexible, jointed construction. The solution was not to encase them in concrete, but to practice what is called retrofitting. This involves carefully removing damaged material, then reinforcing the structure with compatible, sympathetic elements. In Nepal, this meant using traditional wooden pegs and brackets to repair joints, and inserting slender, flexible stainless steel rods discreetly into the core of masonry walls, where they add tensile strength without restricting the natural, breathable movement of the bricks. The goal is to restore the structure's original capacity to flex and dissipate energy, not to change its fundamental behavior. It is a philosophy of minimal intervention, where every new element added is reversible and does not compromise the historic fabric. Another powerful example comes from the ongoing work at the Colosseum in Rome. To stabilize its fragile arches without altering their appearance, engineers inserted titanium supports. Titanium was chosen not for its raw strength alone, but for its compatibility. It expands and contracts with temperature changes at a rate very similar to the original travertine stone, preventing new stresses from developing at the connection points. This is the essence of sensitive restoration, choosing materials that converse peacefully with the old, that work with the stone's natural rhythms rather than forcing it into a new, rigid lockstep. These case studies teach a broader lesson about our relationship with the past. They remind us that preservation is not an act of freezing something in time, but of stewarding its ongoing life. It is about extending the conversation between the building and the earth, not interrupting it with a shout of modern certainty. When we approach an ancient temple with the humility of a student, seeking to understand its logic before applying our own. We do more than save stones. We keep a millennia-old dialogue alive, ensuring that the next time the ground whispers, the temple will still know how to answer. But the greatest strength of a temple was never measured in the thickness of its walls alone. Its true power resided in the human heart. In a world where the ground could open without warning and the sky could turn to fury, the silent, unyielding presence of a sacred structure offered something priceless, a fixed point in a shifting universe. Its physical endurance became the ultimate proof of its spiritual promise. When every other sign of human endeavor lay in ruins after a storm or a tremor, the temple still stood, its columns holding the dawn. This was not a coincidence in the eyes of the community, it was a covenant. The building's survival was read as a direct message, a sign that the divine order remained intact, that the gods were still in residence, and that the community itself was under protection. This created a profound psychological feedback loop, a self-reinforcing cycle of belief and preservation. The temple's resilience through disaster bolstered the faith of the people, and that deepened faith, in turn, fueled an unwavering commitment to the temple's care. Its endurance strengthened cultural identity, and that strong identity guaranteed the structure would never be forgotten or abandoned. Think of a village that watches the floodwaters recede to find their shrine still dry upon its hill. The relief and awe they feel transforms into a renewed, almost sacred duty. Repairing a cracked step becomes an act of gratitude, resetting a fallen stone a communal ritual. The temple transitions from being a place of worship to becoming the central character in the community's story of survival. It is the hero that weathered the storm, the elder that remembers all the past trials. This intangible bond, this psychological resilience, is the invisible mortar that has held these places together long after the original builders were gone. The temple ceased to be just a building of stone and timber. It became a living testament to human perseverance. Its preservation became synonymous with the preservation of hope itself, a tangible anchor for collective memory and identity. To lose it would be to lose a part of the soul, to admit that chaos could win. So generation after generation they returned. They cleared the debris, they mixed the traditional mortar, they passed down the stories of the great shaking and how the temple held. In this light, every act of maintenance was a reaffirmation of faith, not just in the gods but in the enduring spirit of the community. The stones stood because the people believed they must, and the people believed because the stones stood. This silent partnership between belief and masonry, between hope and limestone, may be the most powerful seismic secret of all, the unshakable human need for a sanctuary that whispers against all evidence you will endure. Before blueprints there was ballad, before textbooks there was tale. The deepest seismic wisdom of the ancient world was not stored on clay tablets or papyrus scrolls, but in the very breath of the community, in the stories told around fires and the chants sung by masons as they set a cornerstone. This was a living, breathing knowledge system where hard-won empirical data was encoded into myth, song, and proverb to ensure it survived the ravages of time and memory. A culture's most vital survival strategies were woven into its folklore, transforming abstract physics into memorable narrative. Consider the widespread motif of a dancing god or a trembling mountain spirit found in the earthquake lore of cultures from the Pacific Islands to the Andes. On the surface, these are spiritual explanations for a terrifying natural event. But listen closer to the descriptions, the specific language used. A deity described as rocking side to side or a spirit said to make the temple sway like a tree could be a precise, observational account of how a well-built structure actually behaved during a tremor. The storytellers were not just crafting myth, they were reporting data, noting that the building oscillated and returned to center, a performance so miraculous it could only be attributed to divine intervention. The story became a vessel carrying the critical observation that a flexible, swaying motion was associated with survival, This encoded knowledge then guided future builders, who understood through the parable that a temple should be built to embody that sacred, life-giving dance. This oral engineering extended to the very ground upon which to build. A proverb passed from elder to apprentice might sound like simple poetry, a warning to avoid the ground where the water sleeps or to seek the hill that sings to the bedrock. To modern ears, this sounds like mystical nonsense. To a master builder listening centuries ago, it was a densely packed technical manual. The ground where the water sleeps is a brilliant, intuitive description of a high water table or soft, saturated soil, conditions that can liquefy during an earthquake, swallowing whole structures. The hill that sings to the bedrock might describe a stable, rocky outcrop that produces a specific, solid sound when struck, indicating a firm foundation. These sayings were mnemonic devices, catchy and easy to remember, ensuring that generations of builders who might never learn to read would carry this essential geotechnical wisdom in their minds. A folk song about a village lost to a landslide might meticulously describe the shape of the valley, the type of trees that grew there, and the season of the rains. Within that tragic melody was a complete case study in slope instability, teaching listeners to recognize the warning signs in their own landscape. The rhyme or rhythm made the information sticky, allowing it to survive wars, migrations, and the slow erosion of centuries. Decoding this folklore today offers historians and seismologists a remarkable new lens. It allows us to cross-check the physical evidence of the stones with the narrative evidence of the stories. When a geological survey confirms that a 1,000-year-old temple was, in fact, built on a stable spur of bedrock, and the local oral history contains a founding myth about choosing the voice of the stone over the whisper of the river, the correlation is powerful. It suggests the builders made a conscious, scientifically informed choice, and then enshrined that choice in legend to guide their descendants. This transforms our understanding of these traditions from primitive superstition into a sophisticated, culturally embedded form of data transmission. The myth was the backup drive, the song was the cloud storage, ensuring that even if every written record was lost, the essential lessons of resilience remained in the language, the liturgy, and the lullabies. It represents a profound trust in collective memory over individual genius, a recognition that for knowledge to truly endure, it must become part of the story a people tell about themselves. We are now learning to listen to these old stories not just as folklore, but as the first seismic reports ever filed, written not in numbers but in the enduring poetry of survival. A world map of ancient temples reveals a stunning pattern of parallel thought. In the misty highlands of Peru, the Inca shaped mountains into terraced foundations. On the earthquake-prone islands of Japan, carpenters built wooden pagodas to sway like trees. In the arid heart of Turkey, builders at Hattusa used giant stone foundations that could rock independently. These civilizations were separated by vast oceans and millennia, with no possibility of sharing blueprints or engineering notes. Yet when faced with the same terrifying force of a shaking earth, they each arrived at a remarkably similar set of solutions. This is not a coincidence, it is a powerful testament to convergent human ingenuity, a global chorus of different cultures singing the same song of survival, each in their own architectural language. They were all reading from the same universal textbook, the laws of physics, and their solutions, though born in isolation, echo each other with uncanny clarity. The floating foundation is a perfect example of this global echo. In Japan, the Shinbashira pillar hangs like a pendulum in a pagoda's hollow core. In ancient Greece, builders laid the lowest courses of temple stones on a bed of sand or gravel. The materials and the scale were different, one was wood and the other stone, but the underlying principle was identical, to decouple the structure from the violent motion of the ground. Both systems understood that to save the whole, you must allow a controlled, isolated movement at the base. it is the same brilliant insight discovered on opposite sides of the planet. Look at the use of flexibility. The interlocking stonework of Machu Picchu, where blocks grind and settle during a tremor, finds its conceptual twin in the complex wooden bracket systems of Chinese and Japanese temples, the Dugong and Tokyo. Both are designed not for absolute rigidity, but for a calculated give, a way to let the building breathe and shift without breaking its bones. The energy of the earthquake is dissipated not by resistance, but by absorption through friction in stone or the flexing of wood. Again, the material culture could not be more different, but the intellectual leap is the same, a recognition that brittleness is the enemy of longevity. This global tapestry even extends to the concept of sacrificial elements. The bronze clamps in Greek temples, designed to bend and fail first, protecting the stone, mirror the philosophy behind traditional masonry in many parts of the world where a specific type of mortar or a wooden lintel was intentionally made to be the weakest link. The goal was never a perfect, unblemished survival, but a managed, repairable one. This pattern of independent discovery points to something profound about the human relationship with challenge. When survival depends on understanding a fundamental force of nature, the human mind, through careful observation and iterative experimentation, tends to walk down similar paths of logic. It suggests that resilience is not a cultural trait, but a human imperative. Faced with an unpredictable and powerful environment, communities separated by geography and belief all gravitated toward the same physical truths: balance over rigidity, flexibility over strength, and planned redundancy over fragile perfection. Mapping these strategies creates a hidden network, a web of wisdom connecting sites we never thought to link. The pyramids of Egypt, the ziggurats of Mesopotamia, the cliff dwellings of the American Southwest, and the stone circles of Europe all can be seen as local dialects in a global conversation about stability. They each ask the same urgent question of their landscape: how do we build a sanctuary that lasts? And through trial, observation, and deep respect for their materials, they each arrived at answers that resonate with the others. This silent, global consensus, written in standing stones and enduring wood, offers us a humbling and hopeful lesson. It tells us that the drive to create safety and meaning in a chaotic world is a universal thread in the human story. Our ancestors, listening to the same earth, often heard the same whispers and translated them into shelter. Their legacy is a global library of resilience, its shelves made of mountain terraces and its pages written in interlocking stone, waiting for us to read not just the individual stories, but the collective truth they all proclaim. The final blueprint for a pyramid was never a parchment scroll. It was a miniature world held in the hands of a master builder. Across ancient cultures, from the banks of the Nile to the highlands of the Andes, we find the silent partners of monumental construction, small-scale models crafted from clay, wood, or stone. These were not mere decorative trinkets or votive offerings, though many were found in tombs. They were functional prototypes, the ancient world's equivalent of a three-dimensional sketch and a wind tunnel test, combined into one tangible object. Before committing 1,000 workers to a decade of quarrying and hauling, the architect could first test his vision on a tabletop. He could feel the weight distribution in his palms, assess the slope of a wall, and visualize the interplay of mass and void. A clay model of a temple complex, for instance, allowed for the precise planning of courtyard spaces, the alignment of gateways, and the critical relationship between individual structures. This tactile experimentation provided something no drawing could: an intuitive, physical feedback loop. By building a small version, the builder could literally shake the model, observing how its components settled, where stress points might appear, or if the proportions felt inherently stable. It was a form of empirical research, a slow, careful conversation between idea and material. This practice reveals a crucial truth: their engineering was a deliberate, iterative process of trial and refinement. A design was not simply copied from a previous generation. It was prototyped, assessed, and optimized. Imagine an Inca architect working with a small stone model of a terrace system. He could stack and restack the tiny stones, experimenting with different interlocking patterns to see which assembly felt most secure when the table was gently rocked. He was running a seismic simulation with the tools he had, learning through direct manipulation how forces travel through a geometric network. This iterative prototyping demystifies the leap from concept to colossus. It bridges the gap between the spark of an idea and the mountain of cut stone, showing a methodical, problem-solving mindset. The model was a safe space for failure, where a flawed concept could collapse harmlessly in a handful of clay, saving years of labor and immeasurable resources. It turned abstract principles of stability into a physical language anyone could understand and critique. When we look at the perfect, enduring proportions of a great temple, we are not looking at a happy accident of tradition. We are witnessing the final, full-scale iteration of a design that was tested, tweaked, and proven in miniature long before the first foundation stone was blessed. This humble practice of modeling underscores that ancient engineering was a science of the hands as much as the mind, a discipline where seeing was believing, but touching was understanding. The true cost of a temple was measured not in gold, but in generations. To raise a structure capable of defying earthquakes required a staggering investment, one that could only be sustained by the very fabric of society itself. This was a project that dwarfed any single lifetime, demanding a continuous flow of labor, materials, and food for workers on a scale that would challenge modern logistics. The economic engine behind these marvels was as carefully engineered as the foundations. In centralized empires like Egypt or the Inca, the state wielded a powerful tool known as corvée labor. This was not slavery in the chattel sense, but a form of civic duty or tax, where citizens contributed a portion of their year to state projects. Farmers, during the Nile's inundation when fields were flooded, would be mobilized to haul stone for a pharaoh's pyramid or temple. This system created a rotating, skilled workforce that could be deployed with breathtaking efficiency, turning idle seasons into periods of monumental construction. It was a brilliant logistical solution, harnessing the agricultural calendar to fuel architectural ambition. The materials themselves tell a story of economic reach. The granite for an Egyptian obelisk might be quarried 500 miles upstream, transported on barges during the flood season. The cedar for a temple roof in Jerusalem was sourced from Lebanon, a precious commodity traded over great distances. This procurement was a massive undertaking, a testament to trade networks, royal treasuries, and the sheer political will to command resources from across a kingdom. Every stone, every timber represented a complex transaction of labor and logistics. In the city-states of ancient Greece, the model was different but no less profound. Funding often came from public treasuries, war spoils, or wealthy citizens seeking civic honor. Construction was a point of communal pride, a physical manifestation of the city's devotion to its patron deity. Citizens might vote on designs and budgets, creating a deep sense of collective ownership. The labor was highly specialized, with stonemasons, carvers, and bronze workers forming guilds that passed techniques from father to son. This focus on craftsmanship over speed was critical, as the seismic resilience depended on the precise fit of every joint, a quality that could not be rushed. Whether through imperial decree or democratic consensus, the societal commitment was total. This immense economic effort forged an unbreakable link between the people and the stone. When you have poured a season of your life into hauling a block, or your community's wealth into purchasing the finest marble, the structure ceases to be just a building. It becomes a repository of collective sacrifice and hope. Its permanence is no longer an abstract ideal. It is a personal and civic necessity. The economic investment created a powerful psychological mandate for the temple to endure, ensuring that future generations would feel the same imperative to maintain and repair what their ancestors had given so much to create. The temple's resilience was therefore underwritten by the most powerful force of all, a society's unwavering decision that some things must be built to last forever, no matter the cost. The stones were also speaking a hidden language of mathematics. Beyond the choice of material and the cleverness of joints, ancient architects encoded their temples with a silent geometry, a system of sacred ratios believed to mirror the very order of the cosmos. They built according to proportions like the golden section, where the relationship between parts feels instinctively balanced and pleasing to the eye, or precise Pythagorean triangles, shapes revered for their harmonic perfection. For the builders, this was a spiritual act, an attempt to make the divine blueprint visible on earth. The temple was not just a house for a god, it was a mathematical hymn made solid. Yet this pursuit of celestial harmony yielded an unexpected and profoundly practical gift: structural resilience. Those same perfect ratios often create forms that are naturally strong, forms that manage physical forces with an elegance that feels almost preordained. Think of a well-proportioned arch, its curve distributing weight flawlessly, or a pyramid, its slope channeling massive loads directly into the ground. The sacred geometry was, in many cases, optimal engineering in disguise. This is because certain proportional relationships avoid creating weak points where stress can concentrate. They result in a balanced, coherent whole where forces flow smoothly through the structure instead of fighting against awkward angles or unstable overhangs. Perhaps even more crucially, these harmonic proportions help a building avoid a dangerous phenomenon called resonance. Every structure has a natural frequency at which it likes to vibrate, much like a tuning fork has a specific pitch. If the seismic waves from an earthquake happen to match that exact frequency, the shaking can be dramatically amplified, like a singer shattering a glass with the right note. The building and the earthquake become locked in a destructive duet. The intricate, harmonious geometry of a temple like the Parthenon, with its carefully calculated column spacings and roof dimensions, likely creates a complex set of interacting frequencies that are difficult for a chaotic seismic wave to lock onto. Instead of singing one clear, dangerous note, the structure hums with a chord, a blend of vibrations that tend to cancel each other out or simply absorb the energy without amplifying it. The pursuit of beauty and cosmic order inadvertently built in a form of acoustic defense against the Earth's roar. This reveals a layer of intention so deep it transcends our modern categories. The builders were not thinking in terms of dampening seismic resonance. They were thinking in terms of creating a home worthy of Athena. But their uncompromising standard for harmony, their belief that the temple must be a perfect echo of a universal truth, forced them to arrive at shapes that were inherently stable, balanced, and resistant to chaotic vibration. The resilience was a happy byproduct of a sacred mandate. So when we look upon the serene facade of a classical temple, we are not just seeing art or religion frozen in marble. We are looking at a sophisticated vibration dampener, a seismic firewall crafted from ratio and faith. The stones hold their pose not just because they are heavy or well-fitted, but because their very shape is a conversation with the hidden laws of the universe, laws that govern both the music of the spheres and the stability of the earth. The temple's resilience was a single movement in a much larger environmental symphony. To truly understand its endurance, we must listen to how its design harmonized with every force of its world, not just the trembling of the earth. The orientation of a sacred doorway was rarely arbitrary. It might be aligned to catch the cool, prevailing summer breeze, channeling it through shaded colonnades to naturally ventilate the inner sanctums. This same careful positioning, which broke the force of relentless winds, also presented a streamlined profile to seismic waves, reducing the surface area that a lateral shock could push against. The builders were thinking about comfort and ceremony, but the physics of their choices provided a multi-layered defense. This integration extended to the very skin of the temple. Look at the elaborate, tiered roofs of Southeast Asian temples, sweeping upward in graceful curves. These iconic shapes are masterpieces of hydrological engineering, designed to shed the torrential rains of the monsoon season with incredible efficiency. The rapid runoff prevented water from pooling and soaking into the masonry, which could freeze and thaw or simply add destabilizing weight. But that steep, curved pitch also did something else. It created a roof structure that was excellent at shedding lateral forces. The shape effectively sliced through the push of high winds and the shove of an earthquake, directing those energies up and over the building rather than allowing them to press flat against a solid wall. The solution for one environmental challenge became the secret strength against another. Even the choice of building site reflected this holistic calculus. A temple was often placed on a natural promontory or a carefully terraced hillside, not just for majesty but for practical geology. Such a location offered stable, well-drained soil and maximized airflow, reducing dampness and the decay it brings. But that elevated position, anchored to solid bedrock, also meant it was less susceptible to the amplified shaking that can occur in soft, valley-bottom soils during a quake. The builders were selecting for public health and ceremonial grandeur, yet they were also instinctively selecting for seismic safety. They saw the temple not as a separate object dropped onto the land, but as an organ grown from it, its form and function shaped by a continuous dialogue with sun, wind, rain, and stone. The seismic design was never a standalone chapter in their manual. It was a verse woven into a much longer poem about living wisely in a place. By leveraging natural forces for daily benefit, they inadvertently built a structure that was pre-adapted to survive those same forces at their most extreme. The temple that stayed cool in summer and dry in the monsoon was, by its very nature, already practicing the art of resilience. Its longevity is a testament to a philosophy that asked not how to dominate the environment, but how to join its enduring rhythm. But the full story of resilience is told by both the survivors and the fallen. For every temple that stands defiant, others lie in silent ruin, their stones scattered by the same forces. These failures are not mere footnotes, they are the missing chapters in the ancient engineering manual, the stark lessons written in rubble. The Roman city of Pompeii offers a profound example, often overshadowed by its volcanic fate. Decades before Mount Vesuvius erupted in 79 CE, a powerful earthquake struck the region in 62 CE. Contemporary accounts and archaeological digs reveal widespread damage, with temples, homes, and public buildings collapsing. This pre-eruption quake exposed a critical vulnerability. Many structures in Pompeii were built with a framework of rubble and mortar, then faced with brick or stone. This technique, while fast and economical, often lacked the flexible, interlocking integrity of pure ashlar masonry or the self-healing chemistry of superior Roman concrete. When the ground shook violently, these composite walls could not move as a unified, flexible skin. They fractured at their weak points and crumbled. The disaster served as a brutal, large-scale test, highlighting which building methods worked under extreme duress and which ones catastrophically failed. It was a city-wide lesson in structural integrity, one that the Romans were beginning to learn from when the volcano intervened. Similarly, in the Maya world, not all pyramids share the legendary stability of sites like Tikal. Certain structures, particularly those built on low-lying, swampy ground or atop unstable artificial platforms of loose fill, show clear signs of catastrophic collapse or severe tilting. The failure here was often one of foundation, a misjudgment of the ground itself. In their ambition to shape the landscape, builders sometimes placed immense stone loads on soils prone to liquefaction, where solid ground can turn to a fluid slurry during intense shaking. The pyramid, engineered perfectly above ground, would succumb to a flaw it could not see beneath it. These negative examples are invaluable because they complete the picture. They prove that ancient seismic engineering was not a static canon of perfect solutions passed down unchanged. It was a dynamic, living science of trial and error, a continuous process of learning forged in the aftermath of disaster. A collapsed temple taught the next generation what not to do, which slopes to avoid, which mortar mixes to abandon, which foundation depths were insufficient. Each ruin became a classroom, its broken geometry a problem set for future builders to solve. This reframes our entire understanding. The enduring temples we marvel at today likely represent the refined, successful outcomes of a long and painful process of elimination. They are the answers that survived countless tests. This history of failure teaches a humbling yet hopeful truth. Resilience is rarely a first attempt. It is more often a hard-won prize, earned through observation of collapse and the courageous decision to build again, but differently. The silent stones of Pompeii's quake-damaged basilica or the slumped corner of a Mayan platform are not just evidence of defeat. They are the foundational experiences upon which all later success was built. They remind us that the path to standing for millennia is paved with the lessons of what fell. A single crack in a 2,000-year-old column is not a flaw. It is a testimony. Across the ancient world, temples and monuments stand as silent witnesses to every tremor that has ever shaken the ground beneath them. But they are not passive witnesses, they are meticulous record keepers. Every stone out of plumb, every lintel with a fresh patch of mortar, every foundation that has settled unevenly holds a story. Unlocking these stories requires a unique kind of detective, one who speaks the language of both earthquakes and history. This field is called Archaeoseismology, and it turns ruins into the most durable seismographs ever built. Think of an archaeoseismologist as a forensic scientist at a crime scene that is centuries old. Their evidence is not fingerprints or fibers, but the architecture itself. They begin with the most obvious clues, the catastrophic ones, a row of massive columns that have all toppled in the same direction, like dominoes frozen in mid-fall, tells a clear tale. By mapping the direction of the fall, scientists can trace the path of the seismic wave that knocked them down. It is a vector arrow written in marble, pointing back to the epicenter of a forgotten disaster. But the most revealing evidence is often more subtle. It is found in the repairs. Look closely at the masonry of an ancient temple, and you might see a vertical seam where the stonework changes. The blocks below the line are weathered and original, while those above are slightly different in color, size, or craftsmanship. This is a repair line, a permanent marker of where the wall cracked and was later rebuilt. The height of this line above the ground is crucial data. It indicates the level of stress the wall could withstand before failing, a physical record of the earthquake's intensity at that very spot. Multiple repair lines at different heights in a city can map the shaking intensity across an entire ancient landscape, revealing which neighborhoods were hit hardest. Sometimes the evidence is one of ingenious adaptation rather than damage. A classic clue is the rotated column. In many Greek temples, you will find a column that has twisted on its base, its flutes no longer aligning perfectly with its neighbors. This is not a construction error, it is a seismic signature. It happened because the column rocked in its socket during the tremor, and when it settled back, it did not return to its exact original orientation. The direction and degree of that rotation tell the detective about the direction and strength of the ground motion. It is a fossilized recording of the dance step the temple performed to survive. This forensic analysis does more than just catalog past disasters. It provides the ultimate validation for the ancient engineering we have been exploring. When an archaeoseismologist examines a 2,000-year-old temple and finds evidence of a massive, magnitude 7.5 earthquake in its repaired walls, they are not just seeing damage. They are seeing proof of performance. The structure endured an event that would level modern, unprepared cities. The specific patterns of the damage, or lack thereof, show exactly how the ancient safeguards worked in real time. Did the columns rock in their sockets? The evidence will show it. Did the interlocking masonry shift without collapsing? The stones will confirm it. This empirical data bridges the gap between admiring an old technique and understanding its quantified value. It allows modern engineers to plug real-world, historical performance data into their models, asking not just, could this work, but we know it did work under these exact conditions. Ultimately, these stone scars transform our understanding of history itself. Written records of ancient earthquakes are often brief, poetic, or lost entirely. A chronicle might simply state, and in that year a great shaking destroyed the temple. But the stones tell the fuller, more technical truth. They can date the event through associated archaeology, measure its force, and map its reach. They reveal a community's resilience, showing how quickly and skillfully they rebuilt, often improving their methods with the hard lessons learned. Each crack and repair is a paragraph in a longer narrative of human adaptation. By learning to read this mineral memory, we gain more than just seismic data. We recover the story of a dialogue between civilization and planet, written in the only language durable enough to last for millennia, the patient, testifying stone. The deepest prayers of an ancient temple were not just spoken, they were felt in the bones. Across cultures, sacred spaces were engineered to be instruments, their very stones tuned to amplify chant, music, and the human voice into a resonant, enveloping force. In the subterranean chambers of Malta's hypogeum, a word spoken in one room can be heard clearly throughout the entire complex, a phenomenon of acoustic projection that feels otherworldly. Greek amphitheaters were shaped to carry a whisper from the stage to the highest seat. This was sacred acoustics, a deliberate science of vibration meant to elevate ritual into a full-body experience. But this spiritual engineering may have guarded the temple in a way its builders never fully articulated. It invites a fascinating, though still theoretical, possibility. A structure carefully tuned to resonate with certain sacred frequencies of sound might, by its very design, be naturally resistant to other, more destructive frequencies, like those produced by an earthquake. Think of it as vibrational hygiene. If the temple's architecture was optimized to amplify and sustain the low, steady drone of ritual chant or the ring of a bronze bowl, its physical form would have a specific vibrational signature, a set of frequencies it naturally likes to sing along with. Chaotic seismic energy, by contrast, is a jumble of many conflicting frequencies. The theory suggests that by giving the building a strong, clear vibrational identity, a kind of acoustic anchor, it could help dissipate or scatter the incoherent energy of a tremor, preventing any one destructive frequency from locking on and amplifying. It is akin to a trained singer holding a long, pure note amidst a cacophony of noise, their focused tone creating a zone of ordered vibration. This remains a compelling speculation, yet it underscores a profound holistic view. For these cultures, vibrational energy was not divided into separate categories of spiritual and dangerous. It was a single, powerful continuum. The same physical principles that allowed a hymn to fill a stone vault might also, invisibly, help calm a shaking foundation. This unity of purpose is seen even more clearly in the massive bells that crowned temple towers from Asia to medieval Europe. When rung for prayer, their deep, booming voice called the community to contemplation. But that great bronze form, swinging heavily on its wooden yoke, was also performing a vital structural function. With each toll, the bell acted as a passive mass damper, its immense inertia subtly counteracting wind loads and minor tremors, steadying the tower itself. The spiritual signal and the physical stabilizer were one and the same object. This intertwining reveals a philosophy where every element served multiple, harmonious purposes. Sound was not merely an event happening inside the architecture, it was an active participant in the architecture's endurance. The temple was not a mute container for ritual, it was a collaborator, using the physics of vibration, whether from human voice or swinging bronze, to reinforce both its spiritual mission and its physical permanence. In this light, the ancient pursuit of perfect acoustics appears not just as an art, but as another intuitive layer of seismic wisdom, a way of teaching the stones to sing a song so stable that even the earth's discord could not break its rhythm. The grandest temples did not hold a monopoly on survival. The same profound wisdom that stabilized monuments was woven into the very fabric of ordinary life, into the homes of farmers, artisans, and families. This is vernacular architecture, the unheralded genius of common dwellings built not by royal decree, but by community tradition. In every seismic region of the world, from the steep hills of Turkey to the wooded valleys of Japan, humble houses whisper the same lessons taught by the temples, proving this was a knowledge shared by all. Walk through an old Turkish village and you might see a house built with the Himmish technique. Its ground floor is made of stone, providing a solid, weighty base. But the upper story is a lightweight wooden frame, its spaces filled with a lattice of branches and plaster. This is a textbook example of seismic design in miniature. The heavy stone base anchors the house, while the lightweight, flexible wooden upper story can sway and absorb shock without collapsing. The difference in materials creates a deliberate discontinuity, a shock-absorbing layer that prevents the entire structure from moving as one rigid, brittle unit. It is base isolation and flexible framing scaled down for a family home. Across the world in Japan, the traditional Minka farmhouse operates on similar principles. Its massive, sloping thatched roof is incredibly heavy, yet it is supported by a sophisticated wooden skeleton of posts and beams, connected with complex joints that allow for movement. The entire frame is designed to rock and flex like a tree in a storm. The roof's great weight, high up, actually helps stabilize the house during a tremor, its inertia damping the motion, just as it does in a pagoda. These houses were not designed by architects in distant capitals. They were evolved by generations of families who knew the land and its dangers intimately. They used local materials, wood from nearby forests, stone from local quarries, and thatch from their own fields, crafting them in ways that responded directly to the environmental pressures they faced daily. This is the democratization of resilience. The seismic secrets were not locked away in priestly scrolls or royal workshops. They were living knowledge passed from parent to child, from carpenter to apprentice. Every village elder who showed how to notch a beam for flexibility, every community that decided to build on a stable outcrop instead of the soft riverbank, was participating in this collective engineering project. The principles of lightweight upper stories, raised foundations on stone piers to avoid ground moisture and tremors, and flexible, jointed frames appear in traditional housing, from the stone trulli of Italy to the wooden log cabins of seismic regions. This widespread application reveals something beautiful and crucial. Entire cultures were adapted to life on shaky ground. The knowledge was not a specialty, it was a survival skill as fundamental as farming or weaving. The temple was the ultimate expression, the concert hall where the symphony of stability was played with marble and granite. But the melody was first hummed in the timber and plaster of the common house. It was tested every winter storm, every minor tremor that rattled the dishes on the shelf. The humble dwelling was the living laboratory where these ideas were proven, refined, and made essential to daily existence. This deep cultural integration meant that when the earth shook, the entire community, from its grandest shrine to its simplest home, was engaged in the same silent, graceful dance with the planet. The legacy of the temple, therefore, is not just in its own enduring stones. It is in the quiet confidence of a culture that learned to build everything from the sacred to the everyday as an act of respectful conversation with an unpredictable world. The most advanced seismic lab on Earth might be a forest. For millions of years, nature has solved the very problem of surviving violent, unpredictable forces. A bamboo grove bends in a typhoon, its hollow, segmented stems flexing at the joints, then springs back. The porous, shock-absorbing structure of bone and wood manages immense stress by channeling forces along intricate internal pathways. Today, a new frontier of engineering is looking to these biological blueprints, a field known as biomimicry. Yet in a profound twist, this cutting-edge search keeps pointing researchers back toward the very principles encoded in ancient temples. It turns out our ancestors were not just master masons, they were intuitive biomimics, building structures that behaved like ecosystems. The flexible wooden joints of a Japanese pagoda mirror the give of a tree branch. The interlocking stonework of an Inca wall functions like the scales of a pine cone, allowing movement without loss of integrity. The sacrificial failure of a metal clamp in a Greek temple is a form of redundancy found in biological systems where a non-critical part fails to save the whole. These are not vague metaphors, they are parallel solutions to the universal physics of survival. Ancient builders, through deep observation of their natural world, arrived at designs that modern science now recognizes as optimally adapted to dynamic loads. They built bones from stone and trees from timber, long before we had the words for tensile strength or energy dissipation. This convergence suggests we are not inventing a new future, but remembering a very old truth. The next wave of materials will likely embrace this full circle return. Imagine a building skin made of synthetic, self-healing polymers that mimic the reparative chemistry of Roman concrete, but are guided by embedded nanosensors. Picture a structural frame not of rigid I-beams, but of carbon fiber lattices inspired by the lightweight, incredibly strong geometry of bird bones or spider silk, capable of flexing and then reforming their shape. Artificial intelligence could manage these adaptive systems in real time, acting as a digital nervous system. During an earthquake, sensors would detect the tremor's unique frequency and instantly adjust the tension in cables or the fluidity in magneto-rheological dampers within the walls, tuning the building's response moment by moment, just as a tree adjusts its sway to the wind's changing gusts. The goal is a living architecture, one that perceives, reacts, and learns. This vision moves us beyond the concept of a building as a fortress. The future of resilient design may look less like monolithic steel and glass, and more like the intelligent, responsive structures our ancestors built, but with a conscious, global understanding. It is a future where a skyscraper in San Francisco might share a fundamental design logic with a 1,000-year-old pagoda in Kyoto, both conceived as respectful participants in a dynamic world, not conquerors of it. This is the ultimate legacy of the ancient temple. It offers not just a set of technical tricks, but a philosophical compass. It points toward a future where we build not for dominance, but for dialogue, creating shelters that are finally as wise, as adaptive, and as enduring as the natural world that inspired them. A temple that dances with the tremor teaches us more than just how to build. It teaches us how to think. The deepest legacy of these ancient sites is not a set of forgotten techniques, but a whole philosophy of resilience, one that sees our relationship with the planet as a conversation rather than a conquest. Those master builders did not view the earthquake as an enemy to be vanquished by sheer, unyielding mass. They saw it as a powerful and undeniable voice in the landscape, a reality to be listened to, understood, and respectfully accommodated. Their genius was a shift from a mindset of domination to one of profound dialogue. Instead of shouting down the Earth's power with thicker walls, they learned its language and replied with flexibility, intelligence, and a kind of graceful yielding. This is the quiet revolution written in every interlocking stone and every rocking column. It is an acknowledgement that some forces are too vast to resist head-on, and that true strength often lies in the wisdom of strategic retreat, in the ability to bend so you do not break. This ancient ethos moves us beyond mere engineering into the realm of metaphor, offering a vital lens for our own time. We face a different, slower-moving tremor in the form of a changing climate and deepening environmental crises. The modern impulse, much like the failed rigid wall, has often been to dominate, to control, to build ever higher barriers against rising seas and intensifying storms. But the stones whisper a different strategy. They suggest that long-term survival depends on systems that adapt, that yield where necessary, and that are designed from the outset to harmonize with the inherent dynamics of the planet, not to override them. It is the principle of the flexible foundation applied to our cities, our agriculture, our entire relationship with nature. Can we design coastal communities that work with water's ebb and flow, rather than fighting it with brittle concrete alone? Can we create economies and infrastructures that are resilient because they are diverse and interconnected, able to absorb shock and redistribute strain, much like the network of arches in the Colosseum? The temple's lesson is one of humility and profound observation. It asks us to listen to the world we inhabit, to learn its patterns and its pressures, and to craft our solutions not as impositions, but as thoughtful responses. This is not a call for passive acceptance, but for active, intelligent coexistence. It is the difference between a dam that holds back a river until it catastrophically fails, and a terraced landscape that guides the water, slows its energy, and uses it to nourish the soil. Both are interventions, but one fights a single battle it is destined to lose, while the other begins a lasting partnership. The enduring stones stand as a testament to that partnership. They prove that when we align our creativity with the fundamental laws of the physical world, we create things of breathtaking longevity and beauty. In an age searching for sustainability, this ancient dialogue offers a timeless blueprint, reminding us that the most resilient future is not one we build against the world, but one we build in careful, intelligent conversation with it. A blueprint for the next 1,000 years is already written in the stones we walk past. Our modern world builds with astonishing speed, raising cities of glass and steel in months, yet we measure their expected lifespan in mere decades before major renovation or demolition. The ancient temple stands in silent judgment of this disposable timeline, a testament to a radically different ambition, to create not just shelter but legacy. It whispers a provocative question to every architect, engineer, and planner today. What are we building that our descendants will thank us for in the year 4024? This is not a call for nostalgia, for replicating stone columns in an age of carbon fiber. It is an urgent plea to rediscover the philosophy embedded within those columns, to re-enchant the very soul of engineering with the wisdom of durability. We must move beyond a paradigm where the bottom line and the construction schedule are the primary gods we serve. The temple challenges us to add a new, non-negotiable criterion to our design briefs: intentional longevity. This means designing for graceful aging, for adaptive reuse, and for repair. It means choosing materials not only for their cost per square foot, but for their capacity to endure, to patina beautifully, and to tell a story over centuries. It means celebrating the joints that allow movement, the foundations that float, and the structures that breathe, making resilience a visible, celebrated aesthetic. Imagine a modern suspension bridge where the shock-absorbing dampers are not hidden in steel boxes, but elegantly displayed as part of its sculptural form, a public lesson in flexibility. Picture a school or a hospital built with a lattice of timber that is designed to be easily disassembled, repaired, and reconfigured as community needs change. A building that learns and grows rather than becoming obsolete. This is the new aesthetic of resilience, where the logic of survival is not hidden behind drywall, but is the very poetry of the structure. It requires a shift from seeing buildings as finished products to understanding them as living systems engaged in a long-term dialogue with their environment. This is where ancient insight becomes urgently modern. The vernacular builder knew his materials intimately. He understood how local wood would season and settle, how the local stone would bear weight. Today, we have global supply chains and digital fabrication, but we have often lost that deep, empathetic connection to material behavior. The call is to merge our computational power with that ancient material wisdom, to use our algorithms not just to minimize cost, but to model a building's performance across 500 years of wind, rain, and tremor. It is to ask of every new material we invent, how will it age? Can it be fixed? Does it make the structure more adaptable? Or does it lock it into a single, fragile form? By weaving these ancient principles into the fabric of contemporary practice, we do more than create safer buildings. We rebuild a sense of time and stewardship that our culture has dangerously misplaced. We construct heirlooms for the future, infrastructures that declare our respect for generations we will never meet. The temple's greatest gift is not a set of instructions, but an invitation to think in epochs, to build with a love that outlasts us. Our legacy will be measured not by the height of our towers, but by the patience in their foundations and the intelligence in their dance with an ever-changing world. The final lesson from these ancient stones is not a formula, but a philosophy. Resilience is not a product of defiance, but of profound understanding. It is born from the humility to observe the world as it truly is, to listen to the whispers of the earth, and to build in a spirit of synergy rather than supremacy. The seismic secrets we have walked through are far more than clever historical footnotes. They are a living, breathing legacy, a library of timeless solutions for a world that remains, at its core, beautifully precarious. From the pagoda that sways like a tree to the Inca wall that breathes with the mountain, these structures teach a paradoxical truth. To stand firm through the ages, we must first master the graceful art of movement. This knowledge invites a quiet revolution in how we see the world we have built around us. Look at the skyscraper on the horizon, the bridge you cross each day, the school in your neighborhood. Do they embody this ancient dialogue? Do they speak of flexibility, of repair, of a deep conversation with their place? To value durability is to champion designs that do not fight the planet's nature, but work intelligently within it. It is to support architecture that sees a storm not as a siege to withstand, but as a partner in a long, enduring dance. Let these old stones reframe your gaze. Let them inspire you to ask new questions of our modern landscape and to celebrate the wisdom already being woven back into our cities. If this journey from the past to our future has illuminated a new path, consider joining us for more explorations where history and mystery converge. We would love to hear which ancient secret resonated with you most, which temple's silent story left you in awe. Share your thoughts in the comments below, and together, let's keep this essential conversation alive. Yet for all we have uncovered, the stones still hold their silence on profound questions. How did a master builder in ancient Greece, with no formal mathematics, convey the exact inward lean of a column to his apprentice? How was the precise recipe for self-healing Roman concrete, a secret lost for a millennium, transmitted through word of mouth and hands-on practice alone? This transfer of non-written, tactile knowledge remains one of history's great enigmas. It speaks to a lost pedagogy where understanding was passed not through diagrams, but through the feel of a chisel in stone, the sight of a master's hand setting a joint, and the rhythm of songs that encoded building lore. We can reverse engineer their results, but we may never fully recover the living culture of teaching that made those results possible. Then there are the secrets still physically entombed. Advanced scanning technologies are now peering into the hearts of pyramids and beneath temple floors, revealing voids, hidden chambers, and unknown material composites. What if a long-forgotten damping mechanism, a chamber filled with sand or suspended weights, lies concealed within a monument we thought we understood completely? Each new tool, from ground-penetrating radar to muon tomography, promises to turn these old structures into new books with chapters we have not yet been able to read. The detective story is far from over. Every archaeological dig that uncovers a builder's workshop, every lab that analyzes a fleck of ancient mortar, adds another fragment to the mosaic. A potsherd with a sketch diagram, a ledger detailing the shipment of a unique timber, even the preserved fingerprints in a clay brick, these are all clues waiting to be connected. This open-ended pursuit invites us to a permanent state of wonder. It asks us to walk through an ancient gateway not as tourists viewing a finished artifact, but as participants in an ongoing investigation. The greatest potential of these old secrets lies ahead of us. By continuing to listen to these stones with both our advanced instruments and our humble curiosity, we do more than solve historical puzzles. We gather timeless intelligence for the challenges of our own future. The conversation between human ingenuity and the dynamic Earth is one that never truly ends. It simply awaits our next thoughtful reply.